we proved this before, which is not so hard, okay? And then you look at this monster, okay? The way to get to this is to try and interpret, like try and sift out all the notation and work out what does this signify, okay? And the answer is, well, this is a recurrence relation, okay? This here, what you proved earlier, okay? It's a recurrence relation that connects the integral for n plus 1 with the integral for n, okay? So this is the n plus 1 case, and it's climbing down the ladder. Now when you look at this, what is this and how does it differ from that? And the answer is, look, this is the same, okay, so it's the n plus 1. But instead of this here, you've got I1. So what this is after you take, like a recurrence relation is kind of like a ladder, right? This is the image I gave you before. So this means just climb down to the next step. And from this one, I could climb down to the next step and the next step. And this means what happens after you've climbed down all the steps, okay? So this is the last step down the bottom, or well, I know it could be, but it's a bit trivial as a case. And what this signifies is, what are all the steps that you are taking down the ladder, okay? So, to demonstrate that, here's what I'm going to do. I know this, it's a given. So the next step down is go to n, right? Because it's one less than that one, okay? So here's what I'm going to write. Everywhere I see n plus 1, I should write n, okay? And everywhere I see n, it should be exactly right. So here's where I'm going to go. I'm going to say that should be an n, right? So I'm going down one step, which means here I should have 1 over n minus 1. I have n minus 1. What's over here? 1 over n minus 1 and 2 to the power of n minus 1. Okay, I should have put a multiplication in there. Okay. Now, that's really good. This is what I've done here, okay? I need to keep on going, but obviously I can't go forever. It's in the, I don't know what n is anyway, okay? Yeah. I just have to go far enough to establish a pattern, just like in series and sequences, and then I can use that pattern to get to the end. Okay, I can use that pattern to get to the end. So I've got 1, I've got 2, generally I need 3, don't I? Okay, so my next step is to work out the recurrence relation for n minus 1. 3 steps is enough to establish the pattern. It's a bit boring to write them out, but that's what we're looking for as markers to see, do you really understand how the pattern is progressing? So again, take all the n's, knock them down by 1. So this is going to be here. In minus 1. In minus 2. Okay, 1 over n minus 2, n minus 1 to the power of n minus 2. Cool. Right. So then, dot, dot, dot. Okay. Now, what should be the next term that you do? Or I should say, what should be the last term? Okay. Now, you have to think about this, right? Where you're going to end will have an I1 in it, right? You don't want the last one to be an I0, okay? Partly because, like, I0, like, what's the point? 1 minus 1 over x to the power 0. It's... Yeah, that's right. Okay, yeah, good. Oh, you got values. So you know the endpoint, right? So therefore, being that this is one more than this, right? This one over here, my final one, the recurrence relation, sorry, dot, 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 that I should be working out now should have 2 on the left-hand side. Because if I have 1 here, then 0 will be here. Is that right? So I'll do this for 2. So that gives me 1 over 2, I2, equals, now this will be 1 over 1, I1, minus, okay, what's this thing in here? This will become 1 over 2 times, sorry, 1 times 2, sorry, you're right. 1 times 2 times 2 to the power of 1. Is that right? And now you can kind of see why it's not just arbitrary, it has to end at 1, because if it ended at 0, you'd have 0 there, okay? So this is the bottom rung. I've gotten there, okay? I have all of the steps of the ladder now laid out in front of me, and this is what I have to prove. I have to prove to get from the n plus 1th rung all the way down to the bottom rung. This is what you have to do, okay? So, I think I have some space over here. I start off with my, my beginning here, right? This is the whole integral, okay? Now, I know that it's equal to this, okay? But I'm just going to hold off on writing this because I know what this is equal to. It's equal to the next rung down, right? So I'll pause from writing that for a second. I'll write the other bit, because that's I can evaluate that part. So that's going to be minus 1 over n plus 1 to the n, okay? Plus this. But I know what this is, it's this. So I can start to write this line, but in just the same way that I did it before, I'm going to skip writing this, because I know what it's equal to. Yeah. And I'm going to write this part, right? Because I know what it's equal to. Minus 1 over n minus 1 and 2 to the n minus 1. So now I have to write this part, but I know what that's equal to. Yeah. Okay? So then I'll have this minus 1 over n minus 2, n minus 1, 2 to the n minus 2. And then, where am I? I need to write this. Well, they're all going to be the same. Where I'm going to end is here. So I minus this, minus this, minus this. Minus dot dot dot. The last thing I subtract is that one. So I've finished off my pattern here, right? And then I have to add on I1. Because I don't have an I1 down here, so I actually have to put it on. He actually does appear, which is why he's right there. Okay? Okay, now you look at this and you think, okay, this I can work with. The only thing out of this whole thing that's positive is I1. So you write him out the front. Yeah. And then all of these are negative, so I might as well take a minus sign out of the whole thing. Okay? And again, I want sigma notation here. So I should write it in a more helpful order, namely an ascending order. So I should start here. I'm going to reverse everything. So I'll start with him. Right? And because I've taken out a factor of minus 1, these will now be all added. And now I'm going to go in reverse. So this should be 2 by 3 by 2 squared. And then I just need the third one to establish the pattern. So this would be 3 by 4 by 2 cubed. And where am I going to end? I'll go all the way here. Close bracket. Okay. So that there, reversing the order and taking out the negative sign, now I think I've made it sufficiently clear that that fits sigma notation. So I can now say I1 minus, okay, and I can just pull this guy out. And pull him out. So I go the sum of 1 to n of r plus 1 to the r. Right. So that's good. That's manageable. That's recognizing that it's a recurrence relation, and what they're asking us to prove is now get rid of all the recurrence relations, or at least get rid of all the ones you can until you get to the bottom. Okay? As we will work out in a second, I1, you replace that with 1, we can calculate that. That's an integral we can actually evaluate. Okay?